Hello guys, welcome back. We're in video 3 of 3 from lesson number 5, Implicit Differentiation. I'm going to do just 3 more problems with you. These 3 questions just require a little bit more thinking and a little bit more algebra skills. So they're not necessarily hard problems to do, it just requires a little bit more thought. So I'm also assuming that you know how to take derivatives implicitly. So if you're not comfortable with this, go back and look at video number 1 and make sure that you guys are good with that before we move on here. Okay, so reading question number 11, it says find all points x and y on the curve x to the 2/3 power plus y to the 2/3 power equals 8, where the slope of the tangent line to the curve is -1. So a couple cool things that we're just going to figure out right now off the bat is the fact that it's telling us where's the slope of the tangent line equal to -1. So it's telling us this value. So what that means is that dy dx, we're automatically telling you that this value is going to be -1, right? We already know that. So that's the good, important part of this. So that expression, whatever expression we get for dy dx, we're going to set that equal to -1. All right? So that's the first thing we're going to do. The second thing is if we look over here at a picture, we know that the slope of the tangent line is -1. So there's only 2 places that we have negative tangents, and that's going to be one right here, and there's going to be one right here. So we know that our answers are going to be in quadrant 1 and in quadrant number 3. If I do a tangent line to the curve here, they're always going to have a positive slope, right? They're all positive. And same thing with this. This is always going to be a positive slope. So I know it's going to be in quadrant 1 and quadrant 3. So let's go ahead and get started. The first thing we're going to do is we're going to take these derivatives implicitly. So I'm going to do 2/3 x to the -1/3. So that's our first derivative using the power rule. And then we're going to take our derivative of y to the 2/3 power, and we're going to do, again, 2/3. We're going to do y to the -1/3. Now, ladies and gentlemen, remember that because we took the derivative of a function in terms of y, we have to add dy dx. And then we're going to take the derivative of our constant, which we all know is going to be 0. Okay, pretty much be 0. So the first common thing that I think that we can do here is just divide everything by 2/3, right? Just very straightforward. 2/3 is going to go away, so we're really happy with that. And then the next thing is we want to get this by itself, right? We want the dy dx by itself, so we're going to move the x squared over, x to the -1/3 over. And so I'm going to go ahead and just keep the powers now positive. So we have this. And then what we're going to end up doing is we're going to multiply by y to the 1/3 power. So our expression, the expression for this, dy dx, is going to be equal to negative y to the 1/3 over x to the 1/3. Okay, so that's going to be what it is. It's telling us that this value is equal to -1, right? So now we know that dy dx is equal to -1. So I can go ahead and substitute in that this is -1. And now we just have to do a little bit more work. Well, we can cross multiply here. The other thing that I'm going to do is I'm going to go ahead and get rid of the negatives. So we're going to cross multiply here, and it's going to say, all right, well, then x squared, or x to the 1/3 must be equal to y to the 1/3. So really what that means is that x must be equal to y, right? So that's generally what's saying is that when x is equal to y on this expression, then the slope of the tangent line is going to be equal to -1. Well, again, how do we find the actual points themselves? Because x equals y for every value. But we have our fun little equation that's right here. And so what we're going to do is we're going to, and it doesn't matter which one we're going to do, so we're going to do x to the 2/3 plus x to the 2/3 is equal to 8. And we're going to solve this expression, right? Because x is equal to y. So we're going to do 2, and this is now basic algebra, right? Is equal to 8. So we're going to get x to the 2/3 is equal to 4. And so in order to solve for x to the 2/3, we have to raise everything to the 3/2 power. And so remember how we do this. We get x, and I always tell students take the square root first. Take this bottom part, take the root, so that's going to be 4. Take the square root of 4, which is 2 cubed is going to be 8. So x is equal to 8. So we know that this one's going to be 8. And again, because x is equal to y. And so we know that since this is in quadrant 1, we know this value right here, x and y still have to be equal to each other. Well, remember that since it's x to the 2/3 power, we have a positive square here, so we also need the negative 8 and negative 8. So if I went ahead and plugged in negative 8 to the 2/3 power, I'm still going to get the same answer as positive 8 to the 2/3 power because I'm squaring it first. Okay, so that's the answer to question number 11. So let's summarize what we did there. We took our function, we implicitly differentiated it, we solved for dy dx, we knew that that value was equal to -1, and then we got an expression, a general expression for the relationship between x and y. If this had been y equals 2x, then up here for y, we would have substituted in 2x. So it doesn't have to be equal to each other. Once we do that, we now figure out what our points are. It's 8, 8, and -8, -8. Okay, so let's move on down to question number 12. Okay, so part A says show that the slope of the curve at any point is given by this expression. So really what this is telling us is they're giving us the actual answer. They're telling us that this expression is dy over dx, and they just want us to implicitly differentiate this and verify this answer. This is actually a really awesome question, and this has been in an FRQ on an exam before, is that they just want students to realize that all you got to do is implicitly differentiate this and then just verify that you get this answer back. And so let's do it. So we're going to go and get the derivative of x squared is 2x. Again, ladies and gentlemen, I'm hoping you're going to know what I'm about to tell you here. We have to use what rule? The product rule, right? We have to use the product rule for this one. So it's going to be the first times the derivative of the second plus the second times the derivative of the first. Okay? So that's the product rule for this particular problem. We're going to do 2y. And again, because we're taking the derivative in terms of y, it's going to be dy over dx. And just like before, we take the derivative of a constant, we get 0. So we're just going to start simplifying. So the first thing that I'm going to do is I'm going to put the 2x and the y on the other side. So I'm going to do x dy dx plus 2y dy dx. So what I'm doing is everything that has a term that is a dy dx, I'm going to leave it on one side, and then everything else, I don't care if it's x or y, so I'm going to put it on the other side. So then I'm going to move over the negative 2x and then minus y. And then I'm going to undistribute, right? So over here, I'm going to do a little side note for this. I'm going to undistribute my dy dx, so I'm left with x plus 2y. So if I would distribute this back in, I would get this back. And so finally, dy dx is equal to, right here, our negative 2x minus y, all over what we've undistributed, which is going to be x plus 2y. So students actually like these type of questions because it actually is telling you the answer. Again, ladies and gentlemen, I said this in the video number 2, that if you got dy dx and you got something like y plus 2x over negative 2y minus x, and you realize that every single sign is different than what you have, you're fine. You just want the other direction. So instead of me leaving the dy dx's on the left and moving these over to the right, I moved the dy dx's to the right and left these here. So it's okay. As long as all 4 signs are different, then you can just say, okay, let's multiply top and bottom by -1, and then you get back your answer. Okay? So here's our problem. And this is find the points on the curve, the x and y values together, where the line tangent to the curve is vertical, right? Where the time is vertical. So that means that the slope of the tangent line is a vertical line. Well, hopefully you guys realize that the slope of this line, right, is undefined. If this is horizontal, so if this had been horizontal, and sometimes it is, then you're going to set your derivative equal to 0. But since it's vertical, we're basically saying that dy dx is going to be undefined. So what does that mean in respect to this? Because this is our dy dx, right? This is our dy dx. So let me change the color up because it's getting a lot of green here. And so when I do this, if I set x plus 2y equal to 0, then that's going to make this derivative unfortunately undefined. If this had been horizontal, then you would have set the numerator equal to 0 because that would have made, and actually let me just write this down. So if it were horizontal, then you would say that dy dx would be equal to 0, and then you would set your numerator equal to your, because I've seen this one a lot too, so you set your numerator equal to 0. So let's do that. So we're going to get x is going to be equal to negative 2y. Okay? So we want to know the actual points. So just like we did with example number 11, right? example number 11, once we had our expression, we went and plugged it back into the original. And that's exactly what we do with 12. That's why these examples are right side by side. So we have x is equal to negative 2y. So everywhere you see an x, we're going to replace this x with the negative 2y. So everywhere you see it. You're going to look at this and be like, oh my goodness, this is going to be crazy. But it's not going to be crazy. It's going to be pretty awesome because look what is going to happen. So all this is going to be 4y squared. Please make sure you guys do remember to square the negative 2. Students always, silly mistake. They always do that. They always write it like negative 2y squared. That is a bad idea to do, right? Bad idea. So I get 4y squared minus 2y squared plus y squared is equal to 27. I get 4 minus 2 is 2 plus 1 is 3. I get 3y squared is equal to 27. I get that y squared is equal to 9. And I get that y is equal to positive and negative 3. Okay, so y is positive and negative 3. So I know that I have two answers. So I have that where y is equal to 3. And I've got one more y is equal to negative 3. Again, ladies and gentlemen, all you have to do is plug in 3 to y. So you're going to get x squared plus x times 3 plus 9 is equal to 27. Okay, once you do that, you're going to get that this answer is what? X is going to be negative 6. I know you guys can do this without my help, so you solve it. And then if you plug in negative 3 to your function, you're going to get the answer is positive 6. Okay, so these are your answers to your problems for this problem right here. So negative 6, 3, and 3, negative 6. Sorry. Negative 6, 3, and 6, negative 3 is our answers. All right, so those are the 2 points that's on this curve that's going to have a tangent line that is undefined or vertical. All right, last question of the lesson, our fun little crazy problem that we have here. When we get to polar graphs, then you guys will see this a little bit more. This is clearly in rectangular. But we can find the equation that's pretty easily using polars, but that's for another day. Let's look at this function. It says find all points on the graph where dy dx is equal to 0. All points. So again, looking at our picture, we know that we're having 1, 2, 3, and 4, right? Because this is saying where our derivative is 0, which means we have a horizontal tangent. A horizontal tangent. Right? Okay, it's horrible handwriting. I'm so sorry. So again, first thing we're going to do is we're going to take this derivative implicitly, and this is going to be a little bit of fun. So here we go. So again, left side, we're going to use the chain rule. We're going to do 2. We're going to do x squared plus y squared to the 1 power, right, to the 1 less power, and then we're going to multiply by the derivative inside the parentheses. So it's going to be 2x plus 2y dy dx. All right, so remember again, I've said this so many times now, whenever you're taking the derivative of a function that has a y in it, you also need to do dy dx. And then on the right side, we're going to do 4x, and then minus 4y dy dx. Okay, so what we're going to do now is pretty awesome because we know that this derivative is equal to 0. We know it's 0. So we want to know where it's 0, right? So we can go ahead and eliminate this term, and we can go ahead and eliminate this term. Okay, so that's going to kind of be weird right now because we still got x's and y's, but hear me out. So that's okay. We're good with that first step. So let's move on to the next part of this. So let's kind of simplify this a little bit more. All right, so let's simplify it a little bit more. So you guys can see that we have a 2 and a 2x, and so I'm going to go ahead and just do 4x. And I'm going to show pretty much every step, you know, because I just want to make sure that I don't lose people with this, which is equal to 4x. Okay, so let's go ahead and then move the 4x to the left. Okay, like so. And then we're going to factor out a 4x. And you see this. Okay, we see that. So let's look at this and now think about what the question is asking. Because like I said at the beginning of the videos, this is where we have to think a little bit about what's going on. So in this particular example, if we want to continue on with this, all right, well, one of the conditions is, well, when is x equal to 0? Right, when is x equal to 0? And then the other one is when x squared plus y squared minus 1 is equal to 0. Or where x squared plus y squared is equal to 1. All right, so those are our conditions. If x is equal to 0, and then where x squared plus y squared is equal to 1. Those are where, if you guys again look at this problem, our slope of our tangent line is going to be at 0. All right, so let's look at our two conditions, right? So x equals 0. So again, if you guys look over here at the graph, where is x equals 0? Well, x equals 0 is going to be right here, right there. So x equals 0 is right here. X equals 0 is right here. So they don't actually give us a horizontal tangent line. So that one is not in play, right? We're not looking for the actual tangent lines like this. We want horizontal, not the vertical ones. So x equals 0 is out. So this is the only condition that we care about. Well, we have to then go back up to our original. So just like before, we have our conditions, like the first two examples, we have our condition. Now we have to go back to the original. Well, what's really cool here is that x squared plus y squared, which you see right here, it's equal to 1. So I can rewrite this as 1 squared, 2x squared minus 2y squared. Okay, so now that we've written up 1 squared equals this, remember this is derived from this equation, right? This is derived from this equation. So then, even though we used this equation to simplify this down, we technically haven't used this equation yet. So we can also say that y squared, and it doesn't matter which one you solve for here, y squared is equal to 1 minus x squared. So I've now got two equations that I have, two separate equations that I've done, one by the original function, one used by the derivative to actually get myself a system of linear equations. And now if I know that y squared is equal to 1 minus x squared, then I can substitute in, and I can say that 1 is equal to 2x squared minus 2 times 1 minus x squared. And now, ladies and gentlemen, we're happy with this because now everything's in terms of x. We can solve this pretty easily with our problem, and we can look at what values this gives us. So we're going to give you 3 is equal to 4x squared. So x squared is going to be equal to 3 over 4. So x is going to be equal to positive and negative the square root of 3 over 2. So there are four cases, and we have our x values for all of them. Right, we have our x values for all of them. So we have 3 square root of 3 over 2 for our first quadrant. We have square root of 3 over 2 for our fourth quadrant. Right, so that's the first one and the fourth one. Then we have the negative square root of 3 over 2 for our second quadrant, and negative square root of 3 over 2 for our fourth quadrant. All right, so that's the first thing. And then all you have to do, and I'm going to save some time here, is you would then plug in these values back up here to this equation, and then you're going to get 1/2. And they're all going to be 1/2. So this is the first quadrant, there's the fourth quadrant, there's the second quadrant, and there's the third quadrant. Okay, so let's really quickly summarize what the world I just did here. Okay, because let's make sure that you understand these kind of questions. So I took the function and I implicitly differentiated, right? And then I realized that I'm asking you guys where there's a horizontal tangent. Where is my derivative equal to 0? So I went ahead and got out all my dy dx's. And then I got to this point right here. And that's okay. Well, let me go ahead and just kind of simplify this down and see what expressions, like we did for example number 12 and number 13, what expressions do I need? So for number 12b, I needed x equals negative 2y. And for number 11, I was able to do x equals y. So I went ahead and simplified the best that I could to where I wanted two things being multiplied together. Whenever you try to do stuff like this, you always just want a times b equals 0. Or a times b times c equals 0. You want products. Because now I know either this is going to be equal to 0 or I know this is going to be equal to 0. All right. So then when I do that, I get x is equal to 0. Well, I know that's not a criteria because I'm looking for where this function has horizontal tangents. Where at x equals 0, where the graph has points where x equals 0, they're not horizontal, they're vertical tangents. So I know that's not part of my solution. So I know this is the one that I want. So I realized, oh wait, I can simplify this more. I can get an idea of what this equation is, a relationship between x and y, by plugging in x squared plus y squared equaling 1 here. So this blue equation, this dark blue equation, comes from me just slightly simplifying the original equation. And then I use the equation I found through the implicit differentiation to solve for another relationship between x and y. So I solved for y squared. I substituted it back into this equation right here. So this y squared goes into right here. I simplified down, and I got x is equal to plus and minus the square root of 3 over 2. Right? And you guys can see this is a symmetric graph. So how did I know that it was the square root of 3 over 2 for all points? Because you can see this is a symmetric graph. You can see that this point and this point have to be the same value. This point and this point has to be the same value, and they are equidistant from each other. Right? They're equidistant from each other. So then that's how I knew that. And then I took some time and realized, okay, let's plug in the square root of 3 over 2 to your function. You will get positive and negative 1/2. And so I just did it for each quadrant. All right. So this is a crazy equation. It's not something that I would expect to be tested on. However, it's just when we're prepping you guys for higher level math. And so these are the kind of questions that, the higher up you go, the more thinking you'll have to do. And yeah, so we're good to go with that. So guys, lesson 5 is now done. I will come back with you guys in lesson 6. It's one of my favorite lessons of the course, related rates. And we'll get on to now taking implicit differentiation and actually applying it to real world stuff. All right, so I'll see you guys in lesson 6. Take care.